complex functions, limits, and continuity. So let us start from the definition of a complex function. A relation between two sets of complex numbers in which each element of first set is connected to a unique element of the second set is called a complex function. From the definition, it is clear that if we replace the word complex by the word real in this definition, we can get the definition of a real. The main difference between the complex function and real function is that this function is a particular type of relation between two sets of complex numbers, and a real function is that particular type of relation between two sets of real numbers. So that is why we can also define a complex function as a function whose domain and range are sets of complex numbers. If we have a function f from z1 to z2, then z1 is called its domain, z2 is its range. If z1 and z2 both are sets of numbers, then this is called a complex function. And if z1 and z2 are sets of real numbers, then this is called a real function. A complex function is represented by f of z is equal to u plus iota v, where u is a real part of this function and v is called an imaginary part of this function. Here z is equal to x plus iota y is a complex numbers. And let us see some definition of complex function. F of z is equal to x square plus iota y square. This is a complex function. F of z is equal to sine z. This is another complex function where z is equal to x plus iota y. F of z is equal to log z is a complex function where z is equal to x plus iota y. And now let us start from the limits of a real function. Before to define the limits of a real function, let us explain it by an example. In this example, we have a real function f of x is equal to x square minus 4 divided by x minus 2. And we have to find its limits at the point x is equal to 2. Now we can find its limits at x is equal to 2 from left hand side and also from the right hand side. So you can see if I put x is equal to in this function, I will get 0 by 0, which is an indeterminate form. So let us simplify this function. We can use the formula of a square minus b square, which is equal to a minus b into a plus b. And after cancelling x minus 2 with x minus 2, we can get that f of x is equal to x plus 2. To find limits at x is equal to 2, you can see that we can go towards 2 from left hand side. So we can put 1.8 in this function. Then we can go a little more near towards 2 and put 1.9 in this function. We can go a little more near towards 2 and we can put 1.99 in this function, and so on. And we can see the behavior of this function, that to which side f of x is approaching. So let us start from the left hand limit. If we put x is equal to 1.8, we can see 1.8 plus 2. We can get 3.8. So f of 1.8 is equal to 3.8. If we put x is equal to 1.9 in this function, we can get 3.9. If we get put x is equal to 1.99, we can get 3.99. So we can see that as x approaches towards 2, the value of the function is going towards 4. So let us put one more point which is more near towards 2. X is equal to 1.999. And as a result, we can get a number 3.999. So from this we can say that as x approaches to 2, in the result of this, the function f of x approaches to 4. And that is called the limits, which we can symbolically write like this one. Limit x approaches to 2, f of x is equal to 4. This minus sign shows that we are taking left hand limit. And from here we can define the limit of the function. So the definition is that we say that the limit of the function f of x is 4 as x approaches to 2 if the value of the function f of x can be made as close to 4 as we wish. The value of x very, very close to 2. And now let us see the right hand limits of this function. So now we are going from the side of 3. So I will put 2.1 in this function, then I will put 2.01, then 2.001, and we will examine the behavior of this function. So let us put x is equal to 2.1. If I put 2.1 here, 2.1 plus 2 is 4.1. So as a result, we get 4.1. If x is equal to 2.01, it gives 4.01. If I put x is equal to 2.001, as a result, I get 4.001. So we can see that as we go towards 2, the value of the function is going towards 4. And let us put another number, 2.0001. And we can get that the value of the function is very near to 4. It is 4.0001. So we can say that as x approaches to 2, as a result, the value of the function f of x goes to 4. And we can write this in the symbolical form that limit x approaches to 2, f of x is equal to 4. And this plus sign shows that we are taking a right hand limit. And from here we can define the limits of a function. The value, we can say that the limit of the function f of x will be 4 at x is equal to 2 if the value of the function f of x can be made as close to 4 as we wish. Close to 2. Now let us see the definition for the limits of a real function. Here, instead of 4, we use a general number L, and for 2, we use a general number x naught. So the limit of a real function f of x is a real number L as x approaches to a real number x naught. That is, limit x approaches to x naught, f of x is equal to L if the value of the function f of x can be made as close to L as we wish by taking the value of x very, very close to x naught. And now, if we just replace the word real by complex, we can get the definition for the limits of a complex function. If left hand limit is equal to right hand limit, this will imply that limit exists. And now let us see the definition for a complex limits of a complex function. We say the limit of a complex function f of z is a complex number w. As z approaches to a complex number z naught, that is limit z approaches to z naught, f of z is equal to w. If the value of f of z can be made as close to w as we wish by taking the value of z very, very close to z naught. Here we have to note that the main difference in the case of limits for a complex function is that we can take these limits along several paths. And if we have unique solution along all paths, we will say that the limits of a complex function exist. For example, look at this figure number A. In figure A, this is a real number 2, and we can only limits from only two sides. We can come from right hand side, we can also come towards 2 from left hand side. But let us take a complex number and look at figure B. In this figure B, I have a complex number z is equal to 2 plus 2 iota, which is 2 comma 2. So this point is here inside the complex plane. Now I can come towards this point along this red path. This is one direction. I can also go towards this point from the origin along this blue path. I can also go towards this point from a line from this black path, which is parallel to y-axis. Similarly, I can take limits at this point while coming from the above and also from the right hand side. So there are several paths to find limits of a complex function at a point. And if all these limits have a unique solution, we will say that the limit exists. Otherwise, we will say that the limits does not exist. Let us the limits of a complex function by an example. We have to find limits of the function f of z is equal to z square plus z plus 1 as z approaches to 1 plus 2 iota along path 1, which is parallel to the x-axis coming from the right, along path 2, which is parallel to the y-axis coming from above, along path 3, which is the line joining the point 1 plus 2 iota to the origin, coming from the origin. So let us solve this example. Solution of part 1. To find limits of this function, we need three things. We need a function which is given. We need a point at which we have to find its limits, which is 1 plus 2 iota, it is also given. And we need a path which is given parallel to the x-axis coming from the above. So we need this path. So to find equation of this path, let me show you figure number 1. Now, in this figure, first of all, let us represent the point. The point is z is equal to 1 plus 2 iota. This point lies here. We have to find a line which is parallel to the x-axis and coming from the right side. So this red line is that line. We can see it is coming from the right hand side and it is parallel to the x-axis. But we need equation of this line. To find equation of this line, first of all, you have to put z is equal to x plus iota y. Now look at this line. At this line, y is fixed. Y is equal to 2. So y is fixed. But x is a variable. Infinity towards this point. So we can say just put y equal to 2 and z is equal to x plus iota y. So you will get equation of this line, which is z is equal to x plus 2 iota. So this is equation of this line. And now let us find its solution. So along path 1, z is equal to x plus 2 iota and f of x is already given. So we have to put z equal to x plus 2 iota in this function and we can simplify this. And after simplification, we can get square plus x minus 3 plus 2 into 2x plus 1 iota. Now we have to take limits on both sides. The limits are z approaches to 1 plus 2 iota. Now what is z? Z is x plus iota y. So let us replace z by x plus iota y, which means that x is approaching towards 1 and y towards 2. But there is no y in this equation. So we can only use the limits as x approaches to 1. So if I put x is equal to 1, we will get the solution, which is minus 1 plus 6 iota. And now let us find the solution of 2, which is a line parallel to the y-axis coming from above. So first of all, of this line, let us again see another figure. Let us see figure number 2. In this figure, we have to draw a line parallel to the y-axis coming from above. So this green line is parallel to the y-axis. It is coming from above and touching this point. So now we have to find equation of this line. And we can see that at this line, x is fixed. X is equal to 1. Throughout this line, x is equal to 1. But y is changing. Y is coming from infinity towards this point. So just put x is equal to 1 and z is equal to x plus iota y, and we will get equation of this line, which is equal to 1 plus iota y. Now let us see the solution. So along path 2, z is equal to 1 plus iota y, and the function is given in the question. So we have to put this z is equal to 1 plus iota y inside the given function and simplify this. After simplification, we can get 3 minus y square plus 3y iota. And now we have to take limits on both sides. So taking limits, z approaches to 1 plus 2 iota, but you can see on the right hand side, there is no x. So from here, we can only take the limits of y. So y is approaching to 2. If we put y is equal to 2 in this equation, we can get the solution, which is the same, minus 1 plus 6 iota. And now let us see solution of part 3. Part 3 is the line joining the point 1 plus 2 iota to the origin. Let us see from the figure. So look at figure number 3. The line joining the point 1 plus 2 iota, 1 plus 2 iota is the given point, and the origin is 0, 0. So you can see this is the required line which is coming from the origin and joining the origin and this point. So now what we need equation of this line. To find equation of this line, we can see x and y both are changing throughout this line. But from here we can get that x is equal to 1c and y is equal to 2c. So if I put these values and z is equal to x plus iota y, we can get equation of this line, which is c into 1 plus 2 iota. And now you can see that if I put c is equal to 0, I will get the origin. And if I put c equal to 1, I will get this point. So the value of c is between 0 and 1. So c is a 1. And now let us see solution. So now we have to put this point, which is z is equal to c into 1 plus 2 iota. This is the path in the given function. But one thing we have to note here, that after putting this point inside this function, there will be only c. So we need the limits of c. Now as z approaches to 1 plus 2 iota, this implies that c is approaching to 1. In other words, if you put z is equal to 1 plus 2 iota here, you can see 1 plus 2 iota will be cancelled with 1 plus 2 iota, and we can get c is equal to 1. So as z approaches to 1 plus 2 iota, c is approaching towards 1. Now let us put that the value of z in the given function and simplify this. After simplification, let us take limits on both sides. So we take limits z approaches to 1 plus 2 iota, but on the other side, we don't have any x or y or z. We have only c now. So we can take limits c approaches to 1. And after applying these limits, we can get the same solution, which is minus 1 plus 6 iota. So the limits of this function at the given point exist. And finally, let us see the definition of continuity for a complex function. A function f of z is said to be continuous at a point z naught if it satisfies three conditions. The first condition is f of z naught exists. It means that if we put the point z naught inside the given function and simplify this, its answer must not be equal to infinity or minus infinity. So if the answer is not infinity and minus infinity, we say that f of z naught is defined or f of z naught exists. Second, we have to find the limits, and the limits must exist any path. The third one is that the answer obtained from part 1 and part 2 must be equal. In other words, limits z approaches z naught f of z must be equal to f of z naught.